Welcome to the second part of Lecture 4 of Experimental Vibration Analysis. In this video, we discuss hypothesis tests and their use to test stationarity of random signals. The content of this video is found in Chapter 4 of the book Noise and Vibration Analysis. First of all, hypothesis tests are common in statistics to form decisions based on experiments made. Actually, you have often heard results from hypothesis tests, for example when effects of different diets, etc. are presented on the news. As hypothesis tests are not always part of the curriculum in engineering schools, I will go through these tests in some depth. First, a hypothesis test is based on a so-called null hypothesis, which we call H sub naught, and which we try to break. So the hypothesis test can either support or disprove the null hypothesis. An example of a null hypothesis, that one we will eventually use here, is the random signal is stationary. We call the variable that we want to test phi, and we want to test if this variable is equal to some value phi sub naught. We call this the null hypothesis. That is, that phi is equal to phi sub naught. When we will use this test later, phi will be, for example, the RMS level that we use to test for stationarity. The alternative hypothesis, that phi does not equal phi sub naught, is denoted H sub 1, and it's called the alternative hypothesis. Typically, then, we look for a value delta so that the null hypothesis is accepted if the difference of phi and phi naught is small enough. You will see how it works when we do it. Let us assume that the null hypothesis is true. Then we have a case where the probability density of the variable phi that we test, or rather phi hat as it's an estimate, is a normal distribution as indicated in the figure. Actually, more generally, it does not have to be a normal distribution, but it will be in our tests later. But at least we know the probability distribution. We now have two regions. The acceptance regions is between these two limits and is defined so that the tails outside, the area of the upper and the lower tails summed, have an area of altogether alpha, which is called the significance of the test. The rejection region is then composed of the two regions outside the acceptance region. Now, there are two things that can go wrong in an hypothesis test. Here we see the first type of error, which is denoted in type 1 error. This error is that the null hypothesis is correct, but that the value of our variable, by accident so to speak, ends up outside the acceptance region. This leads to the type 1 error. Of course, we can say that the probability of a type 1 error is alpha, based on the drawing. And this value, as I said, is called the significance level of the test, and is usually chosen as a number between, say, 1 and 5%. If we have an incorrect null hypothesis, that is, if H sub naught is not true, then we have the situation depicted here. First, we have the same acceptance and rejection regions, of course. But the difference is that our variable phi does not belong to the distribution centered at phi sub naught, but rather is distributed with some other distribution, centered here at phi sub naught plus d. Furthermore, here we have an area indicated by dashes, which causes the null hypothesis to be accepted, despite the fact that it's not true. So this leads to something called type 2 error. And this has a probability of beta as indicated in the plot here. So the area of this is called beta. 1 minus beta is called the strength of the test. And the test should be attempted to be designed so that the strength is as large as possible. That is, the probability of a type 2 error is as small as possible. We will now see how we can produce hypothesis tests for stationarity. But before we do that, let us define 3 different ways of investigating stationarity of random data. First, we can use frame statistics, which means that we compute, for example, the RMS value of the signal for frames of the data, let's say 1 second at a time. And then we plot these RMS values of each frame as a function of time, as indicated in the plot here. In many cases, this is quite enough to use, together with some engineering judgment, to see whether these RMS values are constant or not. Before going on, I also want to say that stationarity is a tricky subject. Naturally, for any signal on a too short timescale, no data are stationary. So if data are to be considered as stationary or not is therefore to some extent a matter of some judgment. One should ask what the stationary condition is necessary for. And if it's for spectrum analysis, as it often will be in vibration analysis cases, it's reasonable to make the frame size the same as the block size used for the spectrum analysis. This is something we will see in later lectures. Now, in other cases, when we don't think that the frame statistics and some engineering judgment is sufficient, there are 2 different statistics tests or hypothesis tests that can be used to test stationarity. These are called the reverse arrangements test, which tests that there is no trend in the variable phi, and where the variable phi can be either the RMS or skewness or kurtosis, for example. And then there is the runs test, which tests if there are no periodic fluctuations in the variable phi. We start with the reverse arrangements test. Applying this test, first we calculate the frame statistics values. We denote these values y sub I for frame number I. Then we build the variable or triangular matrix H sub ij, which for every ij pair is 1 if yi is larger than yj and is 0 otherwise. Then we sum up the values of H sub ij for all ij pairs in the upper triangular matrix. And this sum we denote uppercase A. If the null hypothesis holds, then it can be shown that the variable A is a Gaussian variable with mean and variance as indicated here. Thus, the limits for a particular significance level alpha can be calculated from a Gaussian distribution so that we accept the null hypothesis if A falls in the interval A sub n 1 minus alpha to A n alpha. The strength of the reverse arrangements tests cannot be known since we don't know the distribution of A in the case that the data are not stationary. There are, however, some empirically determined recommendations commonly used and which I reference in the book. So n should always be larger than 10 and preferably larger than 20. And if n is less than 20, we should use an alpha significance level of 0.1. If the measurement time is between 20 and 100 seconds, then the number of frames should be chosen so that each segment is 1 second long, and the significance level alpha should be chosen as 0.05. And finally, if the measurement time is more than 100 seconds, we should use 100 frames and use a significance level of 0.02. Let's look at an example of a reverse arrangements test. For simplicity, we use only 5 frames, and the RMS of each frame is shown here. Note that this is not a sufficient number, but we use it to illustrate the procedure. Now, to build Hij for all I from 1 to 5 and for j from 2 to 5, we start by I equal 1 and look at the y1 value of 1 here. Is this larger than 1.1? No. Is it larger than 1.2? No, etc. Then we go, in the second row, we go to 1.1. This is yi. Then we compare that with 1.2. It's not larger. With 1.05, yes, it is larger, so we get a 1. And 1.3, no, it's not larger, so we get a 0. And so on until we have filled the entire upper triangular matrix. Then we sum all the 1s, and in this case we obtain an A value of 2. Now, if we let the significance level alpha be 0.1 because we have so few values, and then the limits for our tests for stationarity will be 1 and 8. That you can find in the book. Thus, our sequence is stationary because our A of 2 is in this interval. Perhaps surprisingly, but this is a very small amount of values. Now, it should be rather obvious that the reverse arrangements tests is typically detect if there is a trend in the data, because then Hij will typically either have too many or too few ones. If we go back to the table here, if there is a trend of increasing values, there will be fewer ones than anticipated. And similarly, if the trend is that the signal level is decreasing, then there will be the left values will have a tendency to be higher than the right hand values, and there will be more ones in the table here. This is the idea with the reverse arrangements test. However, if the level goes up and then down again in a symmetric manner, the reverse arrangements test will not detect the data as non-stationary. So then we have a different test. Then we can use the runs test instead. Or really, of course, we should use both tests, and data should be stationary according to both tests for us to call the data stationary. Now, the runs test starts with the same procedure of calculating frame statistics, y sub I. But the next step is to calculate the median of the data. That is the value where there are an equal amount in the series, larger than and smaller than the median value. Then, each value of y sub I is compared to the median, and a plus sign is assigned if y sub I exceeds the median, and a minus sign otherwise. In the next step then, each series of the same sign is noted as a run. And finally, we count the number of runs, which forms a value R. Now, if the null hypothesis holds, if data are stationary, this variable R, the number of runs, will turn out to be a Gaussian variable with mean and variance as shown in the equations here. N1 and N2 are the numbers of pluses and minuses respectively, and thus N1 plus N2 equals the N that is used here. Furthermore, the null hypothesis limits are calculated as for the reverse arrangements test, just using the mean and and standard deviation obtained by these equations instead. Now, since the runs tests is based on the fact that if the data are stationary, then there should be approximately an equal amount of plus signs and minus signs. Now, if there are fluctuations in the values y sub I, then this will lead to a series of pluses or minus signs, and the null hypothesis will eventually be rejected. So unlike the reverse arrangements test, then, the runs test is sensitive to these fluctuations. Here's an example of a runs test. Same values as before. The median in this case will be 1.1, and we then compare the number 1 to the median. It's smaller, so a minus sign. 1.1 is larger than or equal to, so we set it to a plus. 1.2 is larger, so a plus. 1.05 is smaller, so minus. And 1.3 is larger than the median, so a plus. Next, make up the runs. And the first run here is the minus sign. The second run is composed of these pluses. Then we have a third run with a minus and a fourth run with a plus. So all in all, a number of runs of 4. And this will actually fail on a 0.1 significance level. Finally, a few words about normality. Sometimes we assume that data are normally distributed. There are statistical tests for this, but applying them is not very useful. And why is that? Well, first of all, because real data are never Gaussian. The Gaussian distribution includes extreme values in the tails that are usually not found in real data. So usually if you test data for normality, the statistical tests are strong enough to show that no, data are not normal, even if we want to assume that they are normally distributed. So actually, to check for normality, we usually only overlay an estimated PDF with the theoretical PDF, so to speak, using the mean and standard deviation of the data. And then we just judge if we think that the match is close enough. This is about as much as we can do. You could also use the kurtosis value and see if it's close enough to 3, then the data may be Gaussian. Finally, we should mention a couple commands in the Abrovibe toolbox that are important for testing normality and stationarity. First, for testing if data are Gaussian, the command A PDF that we mentioned before can be used because it can plot the PDF of both the data based on a histogram and based on the mean and standard deviation of the data computed. Next, the command framestat can be used to calculate frame statistics using any statistic measure such as RMS or akurtosis, whatever command as input. And finally, the command teststat implements both the reverse arrangements and the runs test methods for hypothesis testing. So this concludes this video. You should now proceed to the video 4C, the last video of lecture 4.